Just a second. All right. Okay. So welcome everybody. So it's a pleasure today to have Christopher Hacon. So he'll tell us about recent progress in the Kähler minimal model program. Please go ahead.
Okay, well, thanks for having me. Thank you all for showing up. From the date here, you can see that this talk is somewhat based on the talk that I gave at Imperial College back in June, but it's somewhat more precise with what I'm hoping will happen in the near future with the Kähler Minimal Model Program. So let me get started. So what's the big goal here? We would like to generalize the results from the Minimal Model Program for projective varieties to the context of Kähler varieties. So ideally, we'd like to prove the Kähler version of the results from BCHM. So what would that look like? So we consider a compact Kähler variety. So X is my compact complex variety. Omega represents a Kähler form. And I'm considering some KLT pair. So I'm assuming that pair is KLT. And there should be two cases. If Kx plus B is big, if this class is big, or more generally, if Kx plus B is pseudo-effective and the boundary is big, then I hope to show that XB has a good minimal model. And I'll recall what that means in a minute. And on the other hand, if Kx plus B is not pseudo-effective, so I'll recall all of these definitions in the next few slides, then I hope to show that XB has a Mori fiber space. So this is the main result from BCHM in the projective case, and I'm hoping that it's true for Kähler varieties. So let me begin by recalling the various definitions in the analytic context, because there are some changes that we need to consider. So the first thing I would like to point out is that divisors can be very rare on Kähler varieties. So instead of considering divisors or Arcatier divisors, I would like to focus on 1-1 classes. But since we're talking about possibly normal, but possibly singular varieties, there's a technical condition that is convenient to impose. We want to consider locally del by exact 1-1 forms. On smooth varieties, you can just talk about closed 1-1 forms, but on singular varieties, you want to actually impose this extra condition. And you should think of this as the analog of the Arcatier condition that we need to impose for divisors. So typically on a Kähler variety, we don't have ample divisors, but we have the equivalent positivity requirement is the Kähler condition. So a smooth real form, 1-1 form, omega is Kähler if it's everywhere positive, and corresponding classes, Kähler classes. You can check if a class is Kähler if whenever you have a subvariety y of your variety x, the integral along y of the k-fixed power of alpha wedged with the corresponding power of a Kähler form is always strictly positive. So this is clearly a necessary condition, but it's also sufficient. And the Neff cone is a closure of the Kähler cone. So you can think of it as being defined by the same, instead of the strict inequality, you will just require the inequality greater or equal to 0 when you integrate against any subvariety y and the corresponding number of wedges of the Kähler form. And I want to emphasize that, in fact, we often talk about a canonical divisor, but that's not really correct. It's not clear that you even have a globally defined divisor. What we're really talking about is the corresponding reflexive rank 1 sheaf. That makes sense. And if this sheaf is Q Cartier, then you can consider the corresponding class in H11 BC of X. Similarly, we have notions of big and pseudo-effective classes. So a big class, alpha is a big class if it can be represented by a Kähler current. So this will be a current which is positive everywhere except where you have these singularities. So in the traditional case, when you have a big divisor, you can always write it as ample plus effective. The corresponding current will have singularities along this effective divisor and will be positive everywhere else. And pseudo-effective just means that you have, instead of having a Kähler current, you just have a positive current. So again, it's in the closure of the big cone. So instead of, so we're going to be working with this group H11BC, and often we just denote it by N1 of X. The Picard number gets replaced by the dimension of the space, and lower one just denotes the dual to H11BC of X. Inside of H11BC of X, we have the Kähler cone, those classes which have the positive intersection with every subvariety Y and wedging with Kähler forms. We note that now, the Neffness condition really is different from the algebraic case because we may have no curves or very few curves to test this against. So instead of testing against curves, right, we've been testing against integrating along a subvariety Y, wedging with a Kähler form to the dimension of Y minus 1. So this sort of has the, it's a N minus 1, N minus 1 form. So it's the kind of thing that you want to integrate against 1, 1 forms, and it plays the role of integrating against curves. So you can think of this as being the generators of your, instead of the cone of effective curves, as the cone of positive 1, 1 classes. So instead of working with the usual pairs, it's actually convenient to work with generalized pairs. So generalized pairs already appear in the projective category, but in that case, instead of using a 1, 1 form beta or a B 1, 1 form beta, we use a B divisor, usually denoted by N, a Neff B divisor. So let me get into the details a bit. So maybe it will sort of tie into the more traditional case. So what's a Neff B11 form? Well, this just means that we have some resolution. On this resolution, we have a 1, 1 form. Closed or locally exact, it's the same because it's a smooth variety. And we insist that this 1, 1 form is Neff, and we can get the corresponding birational 1, 1 form by if you pick any other variety, x double prime, which is birational to x prime, you can consider a common resolution W, and you can just pull back this 1, 1 form from x prime to W and then push it forward. So then you get a corresponding 1, 1 form on every birational model of x. Now, if you're not careful, if your birational model x double prime has sufficiently bad singularities, then the corresponding 1, 1 form beta x double prime will not have will not be locally exact. But that's just the same as when you have an R-Cartier divisor and you push it forward, you might not get another R-Cartier divisor. So there's, this is nothing new. So what's the definition of a generalized pair? So generalized pair consists really of sort of three objects, right? We have essentially on the resolution x prime, we have this Neff 1, 1 divisor, and we have a divisor, a Neff 1, 1 form, and we have a divisor B prime, whose push forward to x is actually an effective divisor, which we denote by B. And we insist, just as in the case of the usual generalized pairs, so in the case of usual generalized pairs, we would insist that this object kx plus b plus beta x is an R divisor, an R-Cartier divisor. That way, we can pull it back and compare it on any resolution. In this case, we're going to insist that I should really be writing the Chern class, but so the corresponding object is can be thought of a 1, 1 form, which is locally exact. Once we've done this, then we can talk about generalized Kawamata log terminal or generalized log canonical pairs by looking at the coefficients of B prime. So let's assume that on this resolution is actually a log resolution. So I can assume that the divisor B prime has simple normal crossing. Then generalized KLT just means that the coefficients of B prime are strictly less than 1. They could be negative on the exceptional divisors. And generalized log canonical means that the coefficients are less or equal to 1. I will be focusing on the generalized KLT case, which is much easier to deal with. One of the reasons why that it's easier to deal with is that one can show that generalized KLT pairs have rational singularities. And that makes things technically a lot easier to deal with. So as in the usual case, you can define the discrepancy of your generalized pair by just taking minus the multiplicities along the corresponding divisor of B prime. So any questions about generalized pairs? Okay, so it's supposed to be the exact straightforward generalization of the usual generalized pairs from the projective setting. Okay, so what does it mean to have a minimal model or a Mori fiber space? We'll say that a generalized pair x b plus beta is a minimal model if kx plus b plus beta x is NEF, a NEF-1,1 class. And we will say that it is a good minimal model if there exists a morphism from x to some other complex variety z and a Kähler form on z such that kx plus b plus beta x is the pullback of this Kähler form. Right, so it's just the analog, it's very closely analog to the usual notion of semi-ampleness. And we say that x to z is a Mori fiber space if, as usual, the relative Picard number is 1, the dimension of x is bigger than the dimension of z, and minus kx plus b plus beta x is relatively Kähler. And so if one is trying to generalize the results from BCHM, it seems to me that it's actually for induction purposes, it's actually convenient to work with a more general conjecture, which includes generalized KLT pairs. So we will consider x, b plus beta a generalized KLT pair, and we conjecture that if kx plus b plus beta is big, or if it's pseudo-effective and b plus beta itself is big, then x, b plus beta has a good minimal model. So you have a birational contraction from x to x prime that behaves well with respect to the discrepancies, improves the singularities, such that on x prime, the class becomes NEF, and in fact, pullback of a Kähler class from some morphism. And if kx plus b plus beta is not pseudo-effective, then we conjecture that we have a Mori fiber space. So we have, again, a birational contraction to x prime, and then we'll have a morphism from x prime to z, such that the corresponding minus kx prime plus b prime plus beta prime is relatively Kähler. So are there any questions on what this generalized conjecture looks like?
Sorry, so actually I have a very basic question. So in the usual algebraic setting, is it easy to deduce this formally from the CHM?
So instead of beta, you have a NEF divisor, essentially, right? And this bigness condition means that you can extract out a little ample, epsilon ample, but NEF plus ample is ample, so you have something that's Q-linear equivalent to that, which is actually honest KLT pair. So it's this generalized form in the projective setting follows immediately from the other form by standard manipulations.
Okay, thanks.
And that was going to be the next thing I was going to say anyhow. So thank you. Any other questions?
Yes. So maybe you were going to also say this, but it seems to me, I mean, this relatively Kähler condition, why don't you just say projective, since the fibers are rationally connected?
Okay, so it will turn out to be projective. It's not immediately clear that what if kx plus b is numerically 0 over the base, then is it clear that there's an ample divisor? I mean, you are right. This is always going to be the case because the fibers are rationally connected. So H20 is trivial, and so if it's Kähler, it has to be projective. Also, it has rational singularity. So you're absolutely right. I'm just not sure if it's immediately obvious or it's a small lemma to prove.
Well, but it's your conjecture. So
Okay, well, okay, that's a question of presentation. Yeah, so
you're not proving anything yet, but okay, yeah, it's fine.
Yeah. Any other questions? Okay, great. Okay. The first comment is what we just discussed, that in the traditional case, it just follows from BCHM. In general, this conjecture seems to be more general because, we're talking about all 1-1 forms, not just our divisors. However, it is possible to show that in the projective case, this result for generalized KLT pairs actually holds and does follow from BCHM. It's not completely obvious. There are several technical details to worry about, and the main input is a Hacon theorem that I'll discuss later. But the key observation is that if X is projective, in fact, these 1-1 forms can be represented by an R divisor plus another 1-1 form that integrates trivially against any curve. So in other words, from the usual numerical equivalence point of view, this 1-1 form is always numerically equivalent in the sense that it has the same integral along any curve to an R divisor. And so then you just apply BCHM to the corresponding R divisor. Of course, you have to show things like, for example, if beta prime is Nef, you have to show that the corresponding R divisor is also Nef. If it's big, the corresponding R divisor is also big. And what's really being hidden here is that you have to also check that the analytic Nefness condition is sort of equivalent to the usual Nefness condition, that integrating against a curve, you always get a non-negative answer. So there are some technical details, but it's not very hard to see that the conjecture holds in the projective case. So turning to the more general Kähler case, in order to establish a conjecture like this, we presumably need to follow the main ideas in BCHM, and we need to have some big proof by induction. And the proof by induction is going to sort of rely on several intermediate steps. Typically, we need to know that the Hacon theorem holds, the contraction theorem holds. Also, essentially, by contraction theorem, I mean the base point free theorem. We need to know the existence of flips, and we need to know the termination of flips, or maybe not of all flips, but of certain sequences of flips. So there's several intermediate theorems that one would like to prove. So let me state those next. So the first one is actually a theorem. So suppose that you have a generalized KLT pair where the boundary is big, B plus beta X is big. Then, in fact, the cone of positive n-1, n-1 classes, so think of this as a generalization of the cone of curves, it sort of splits in two parts. There's the part which is positive with respect to the adjoint class Kx plus B plus beta X, and we say nothing about that. And then there's the negative part, which is generated by finitely many rational curves. So the reason, you're expecting countably many, but note that I've insisted that B plus beta X is big. If I don't insist that that is big, then you'll get countably many that can accumulate along the hyperplane Kx plus B plus beta X equal to 0. And in fact, these are rational curves. So this is somewhat surprising, right? Because this is not a cone of curves. It's a cone of positive n-1, n-1 currents in some sense. And we're saying that the interesting part of this cone, the negative part of this cone, is actually generated by curves. So it is not true in general that if you have a 1-1 class, that it's Nef if and only if it integrates non-negatively against curves. But it is true for adjoint classes Kx plus B plus beta X, where X, B plus beta is a generalized KLT pair. right? So that's the key input in this result. Okay, and so the nice thing here is now we can say that if the class kx plus b plus beta x is not nef, then there is a negative extreme ray, one of these gamma i's, and we can hope to contract that ray, produce our flip or divisorial contraction, and start the corresponding minimal model program. Okay, so this I'll discuss the proof of this result later in what follows, before I want to discuss the various other ingredients. But this holds unconditionally, and I'll discuss the proof in a little while. Any questions about the statement, though? Okay, so the other good news is that the existence of flips is also known in full generality in this context. So if I have a generalized KLT pair and I have a flipping contraction, then the corresponding flip exists. Now, I won't discuss the proof of this result, but let me give you an idea of why it should be true. Well, first of all, what does flip mean? Well, it's the usual definition. The relative Picard numbers, which are defined as the dimension of this H11, are going to be 1 in both cases, minus kx plus b plus beta x, and kx plus b plus beta x plus are both relatively Kähler over Z. So on one side it's negative, on the other side it's positive. And these are all small birational morphism. And in particular, since they are birational, these are Moiré-Chezons, meaning that you can pick a resolution which will actually be a projective morphism. Now, it had previously been established by work of Fujino, also by Das, Hacon, and Pon, that the results of BCHM hold for projective morphisms. So whenever you have a flipping contraction after some resolution, you actually have a projective morphism. So it's not surprising since BCHM holds in that context that we should be able to construct the corresponding flip. So I'm not going to discuss that. I would have to do a whole other talk to explain why the results from BCHM hold for projective morphisms. I've sort of given you an idea why they hold for projective varieties. Projective morphisms is a bit more subtle, but somewhat similar. There are many technical details, unluckily, to worry about. Okay, so flips hold unconditionally. So that's 2 out of the 4 things that we need. I'm not going to say much about termination of flips. Maybe let me discuss it briefly. So it's known that in general, termination of flips is a very difficult problem. It's settled in dimension 3 in the projective case. In dimension 4, there are many partial results. I don't think that the full result is known when kx plus b is not pseudo-effective. I think if I remember correctly, it's completely settled in the pseudo-effective case. And in higher dimension, it's there is partial progress, but it seems to be a very difficult problem. Now, the termination in the analytic case is even harder because, especially for generalized pairs, this 1-1 class is it's not a Cartier divisor, and so if you're looking at things like discrepancies, etc., they're harder to pin down. And it gets very difficult to directly prove termination results for generalized KLT pairs in the Kähler setting. So the idea is to try and mimic BCHM. So we would actually like to instead run a minimal model program with scaling. So again, we don't have any ample divisors, so we can't scale with respect to some ample divisor, but we have this Kähler form, so we can add a big multiple of a Kähler form and start decreasing this multiple until we reach an F threshold, and then we do the corresponding flip and divisorial contraction and repeat. The advantage of doing things in this way is that we obtain a sequence of minimal models for pairs of the form x plus b plus beta plus t. I shouldn't have written this sub x, t omega. And so this is sort of the analog of the minimal model program with scaling in the projective setting. It's very similar to what you would do with a Kähler-Ricci flow. And so what happens is that you produce a sequence of minimal models for objects of this form where t varies in different intervals. And if you were to assume that the minimal model program conjectures work in this setting, then you can formally deduce that you have some finiteness results for these minimal models, and hence you can deduce that this kind of minimal model program with scaling has to terminate. Unluckily, we are trying to prove that result, so we can't use the result to prove termination, right? So all I can say is that this termination is expected, but proving this termination would be a key input in proving the generalized BCHM result in the setting. And what it really boils down to is, you can assume that you know the minimal model program in dimension n-1, and then you want to prove that this kind of sequence of flips with scaling terminates. And so there are several technical issues to worry about, and I'm not going to get into that because it's somewhat involved. The only thing I would like to say is, there's one proof of concept. So in dimension 3, together with Das and Yanis, we do show that this approach does work. So hopefully it works in all dimensions. There are some reasons to be optimistic, but there's several new twists from the projective case. So I'm not going to discuss this. What I would like to discuss is the proof of the Cone theorem and also a strategy for proving the base point free theorem. So I have not mentioned what the base point free theorem is. So the transcendental base point free conjecture is the following. So let's say that we have a generalized KLT pair, and let's say that the class Kx plus B plus beta x is nef and big. Then we hope that this is semi-ample, i.e. we hope that there's a morphism such that alpha is the pullback via this morphism of a Kähler pair. Now, I could have also stated this similarly to the base point free theorem by just saying that alpha is nef and the class B plus beta x is big. The reason I didn't state it, it will be clear in a few minutes, is that we can actually reduce to the case when alpha is nef plus big by using O's result. So I'll mention that in a second. So this is the key case of the base point free theorem that one hopes to prove in the Kähler setting. And of course, one could get greedy and one could hope to prove abundance, but I won't say anything about that. This is known in dimension 3 and not in higher dimensions. Okay, so again, I've sort of mentioned this. Everything I've discussed works for projective pairs. It works in dimension 3. There's some substantial progress in dimension 4 already. So it works for KLT fourfolds, which are numerically effective, equivalent to an effective divisor. So the effective case is now published. And we have significant work in progress for the pseudo-effective case. Actually, not even just a pseudo-effective case for all fourfolds, but the caveat is that we cannot prove that we get a sequence of flips and divisorial contractions, but we get a sequence of weak flips and weak divisorial contractions. So they sort of look like flips and divisorial contractions up to some flops. So it's, they're not as precise as the usual flips. But anyhow, there is substantial work in progress for fourfolds. And so, if we follow the projective the history in the projective case, the next step is to do it in all dimensions, hopefully. So let me say a few words about the Cone theorem and an approach for the transcendental base point free conjecture. And I think that really the transcendental base point free conjecture is the key open question. Once that's settled, I would expect that everything goes through nicely. Okay, so one, I forgot a D here. One nice thing is that we have this recent result of Wenhao O, which establishes sort of the analog of Buxom, Demandie, Pound, Peternel for Kähler varieties. So here's a statement: if X is a Kähler variety, then X is uniruled if and only if K of X is not pseudo-effective. Now, in our setting, B plus beta X is always assumed to be big, or we can reduce to the case where this is big. So if Kx plus B plus beta X is not big, then Kx itself is not pseudo-effective. But then we have a non-trivial rationally connected fibration, let's say F from X to Z. And by a result of Claudon and Horing, this is actually a Moiré-Chuzon map, meaning that you resolve the singularities and blow up a bit, and it becomes a projective morphism. So replacing X by a resolution, we can assume that F is a projective morphism, and then we can run relative minimal model program over Z. Now, there are sort of two obvious cases to consider. If Kx plus B plus beta X is not pseudo-effective over Z, then this will end with a Mori fiber space, so you win, right? Now, it's not clear that if Kx plus B plus beta X is not pseudo-effective, then it's actually not pseudo-effective over Z, right? So this does not cover immediately all cases. However, if Kx plus B plus beta X is pseudo-effective over Z, then this will end with some Kx plus B. Well, it will either end with a minimal model, or in the case that Kx plus B plus beta X is not big, it will end with a Kx plus B plus beta X trivial fibration over Z. Let's call this X prime to Z prime. And then by the canonical bundle formula, you can relate Kx plus B plus beta X to some generalized KLT pair on Z prime. So Kx prime plus B prime plus beta X prime will be the pullback of a generalized KLT pair on Z prime. And since beta prime plus beta X prime was big, you can arrange that BZ prime plus gamma Z prime will be big. And then you can continue an induction on the dimension. So, in fact, proceeding along these lines, you can show that if X, B plus beta is generalized KLT and Kx plus B plus beta X is not pseudo-effective, then eventually you end up with a Mori fiber space. So you have a sort of unconditional result in all dimensions. And otherwise, if Kx plus B plus beta X is pseudo-effective, eventually you end up to the case where a lower dimensional case where in fact Kx plus B plus beta X is big. So really the most interesting case to consider, I'm trying to convince you that most interesting case to consider is the case where Kx plus B plus beta X is big. And because otherwise we can use the maximal rationally connected fibration to start some induction on the dimension. So I'm going to mostly focus on that case. And in fact, typically you can reduce this to the setting where, instead of considering this sort of intimidating generalized pair, you can really think about if you prefer, you can think about a KLT pair, Kx plus B, plus a Kähler form, omega.
May I ask a question?
Yes, please.
Is it possible that Kx plus B plus beta X is big, but X is not projective?
Yeah, of course. Take a general complex torus.
Thank you.
Let's see. Yeah, on the other hand, whenever minus that is big, it will tend to be projective. So, and when minus that is nef, you expect to have some structure theorem, essentially some fiber space of K-trivial variety, or Fano varieties over something K-trivial. So there should be some very precise structure theorems in the anti-nef case.
Could I ask a question about that? Because again, just it seems like almost immediately you reduce to the case where the map is relatively projective because you go to the MRC and then you resolve, right? So
Right. So that's what I'm saying. The interesting case is the non-unirule
okay.
case. And
Because
since I'm assuming that B plus beta is big, the interesting case is the case when Kx plus B plus beta is big.
yeah, but I'm just trying to understand some of the technicalities. So I mean,
Oh,
when
okay.
you run the Kähler MMP in the projective case, you never leave the projective case. I guess that's the point. Relative
Yes.
projective case.
Yes, correct. It's clear that you never leave the Moashizon case, but then so essentially there's two things, there's two possibilities, right? Whenever you have one of your flips or divisor contractions, it could be non-trivial with respect to Kx plus B, in which case it's a projective map, and so you expect to stay in the projective category. And otherwise, it could be trivial with respect to Kx plus B, but then there's some technical considerations that you make that make your life easier. Maybe I won't get into those details.
Thanks.
Okay, so here's a useful result that we need. So we're interested in Neff and big classes alpha. So if the class is not Kähler, then we have seen that the null locus will be non-empty. There will be some subvarieties such that when you integrate along that subvariety, alpha to the d, you will get 0. So it's natural to consider this null locus. And it turns out that this is a closed analytic subset with no isolated points. And you can find a representative of the class alpha, which has singularities, the non-Kähler locus. So you can find a Kähler representative whose singularities are exactly the null set of alpha. So you could think of this, if alpha was a divisor class, you could think of it as finding a divisor whose singularities are precisely concentrated along the null locus. And the idea to prove this result is the following. So you pick a Kähler current in the class of alpha with minimal singularities. Now, it's easy to see that the singularities of this Kähler current have to contain the null locus. And your goal is to show that these two are, in fact, equal. So you pick a maximum dimension component of the singularities of the non-Kähler locus, which is not contained in the null locus, and you're looking for a contradiction. Now, since it's not contained in the null locus, the restriction of this Neff class to V will actually be big, simply because by definition, the of null locus, if it's not in the null locus, the integral along V of the top wedge of alpha will be strictly positive. So that means that this is a big class, so I can find a 1-1 form representing alpha restricted to V, whose non-Kähler locus is strictly contained in V. And now the idea is that you extend this 1-1 form on V to a neighborhood of V, and then you glue it together with the original representative gamma. And in this way, gluing these together, you attain a new 1-1 form whose singularities do not contain V. And that's your contradiction, right? Because you had assumed that gamma was a Kähler current with minimal singularities, and V was a component of these singularities. That's the main idea in showing that this null locus, the key thing here is that I can represent alpha with this 1-1 form gamma, whose singularities are precisely concentrated along the null locus or the non-Kähler locus. So the key point in proving the Cohn theorem is the following. So let's suppose that I have my generalized KLT pair, xb plus beta, and I have Kähler form omega, and I scale it down so that kx plus b plus beta x plus omega is Neff but not Kähler. Then I want to show that there is, in fact, there is an alpha trivial rational curve, which is negative with respect to kx plus b plus beta x. And this will be the generator of the corresponding negative extreme array. Okay, so again, I'm going to be worrying about the big case, but note that if alpha is not big, then this immediately implies that kx is not pseudo-effective, and so one can prove this kind of result just by applying When-Howe's result on the BDP conjecture. Okay, so how does the argument go? Well, so if alpha is big, then I pick this representative of alpha with singularities precisely along the null locus. And now I pick a top-dimensional component of the singularities of this representative gamma, and I look at the log canonical threshold, corresponding log canonical threshold of the pair xb plus beta with respect to gamma at a general point of V. So when I add lambda gamma, I get a generalized pair which is properly log canonical at the general points of V. Then, by a subadjunction result proved with Mihai Paun, we have an effective R divisor B on V, BV, and an FB11 form gamma V, such that BV plus gamma V is big, and when I restrict 1 plus lambda alpha, so 1 plus lambda alpha is numeric equivalent to kx plus b plus beta plus lambda gamma. This is properly log canonical along V, so if this were a usual pair, you would expect to get something of the form kV plus BV plus pseudo-effective. And I'm saying that this kind of adjunction also holds for generalized pairs. Now, I'm not claiming that kV plus BV plus gamma V is generalized KLT, because this is a minimal log canonical center only at the general point of V. It could be very singular at some specific points of V. For example, wherever V meets another component of the non-Kähler locus, I expect it to be quite singular. So this is not generalized KLT. However, BV is an effective divisor and gamma V is pseudo-effective. So, and BV plus gamma V is big, but by assumption, since V is in the null locus of alpha, 1 plus lambda alpha restricted to V is not big. So the only conclusion is that KV is not pseudo-effective. And then by O's result, I know that V is in fact covered by rational curves. And with some work, you can show that these rational curves have the right numerical properties. They intersect kx plus b plus beta x negatively. That's actually pretty obvious because they are alpha trivial and clearly omega positive, so they'll have to be negative with respect to kx plus b plus beta x. This other condition on the length of these extreme arrays is a little bit more tricky, but it follows relatively easily. So any questions about the argument towards the Cohn theorem? Okay, so essentially it follows from looking, once again, sort of to summarize, if your class alpha is not Kähler, then the null locus will be non-empty. We use the null locus to create some log canonical center, and since it's the null locus, the whole class will not be big, and so if the boundary is big, then K of V cannot be pseudo-effective. There must be many rational curves. That's the conclusion. Okay, so now we come to the most speculative part, which is how can one approach the transcendental base point free conjecture? And so, I've started working on this, but I still don't know if... Okay, the best I can say is I don't see any reason why this approach cannot work, but I definitely have not figured out all the technical details. So it's just, at this point, I would like to emphasize that it is just speculations. Some versions of these arguments, I have been able to make them work in some contexts and to prove some theorems, but I'm still on the fence I'm not willing to say that it will lead to a proof of the transcendental base point free conjecture. It seems promising, but I don't know for sure. Okay, so what are we trying to do? So we have a generalized KLT pair where the boundary is big, b plus beta x is big, and kx plus b plus beta x is an F class that I denote by alpha. And what I need to do is I need to define a morphism, let's say G from X to Z, such that my F class is pullback of a Kähler class. Now, again, if alpha is not big, there's a clear strategy. Then we know that Kx will not be pseudo-effective. There's a maximally rationally connected vibration, and I should be able to reduce questions about the class alpha to some other class on Z, which is also an adjoint class for some generalized KLT pair with similar conditions. So this should be a proof by induction on the dimension. There are some technical details, but it seems to be a very good approach. So the real interesting case is the case when alpha is big. In this case, of course, the one thing that we can focus on is the null locus, right? Because if the null locus is empty, then alpha is already Kähler. There's nothing to do. If the null locus is non-empty, what I really need to do is I need to contract the null locus, right? In other words, alpha is Kähler outside of the null locus, and the contraction that I'm looking for, this map from X to Z, is supposed to squish down the null locus, and it should be the identity outside of the null locus. And in fact, what I'm trying to do is I'm trying to contract all alpha trivial curves on the null locus. Now, philosophically, why should I expect that I can contract the null locus? From the previous calculations that I showed you, essentially, you know, the null locus, each component of the null locus tends to have the canonical class tends to be non-pseudo-effective. So each component tends to have an interesting rationally connected vibration, and I am trying to contract along these vibrations, the various components of N, and glue everything together. Okay, so that is very vague. So in more detail, I would like to proceed in the following 3 steps. The first step I would like to do is I would like to define a map from the null locus to some variety W. And then, I want to extend this map to the whole of X. Okay, so here I'm talking about defining a map from the reduced no scheme structure, the reduced space corresponding to the null locus. So what I'm going to do is I'm going to consider the jumping numbers for my pair xb plus beta with respect to this form gamma. Remember, this form gamma has singularities exactly along the null locus. And I'll denote by vi the non-KLT locus of x b plus beta x plus the corresponding coefficient lambda I gamma. And again, I'm not interested in any scheme structure at this point. That will come later. So now I can do the usual adjunction that I discussed before. So let's look at the first log canonical threshold, lambda 1. I take 1 plus lambda 1 alpha restricted to V1. I write it out as kx plus b plus beta plus lambda 1 gamma restricted to V1. I get, by this adjunction result that I proved with Mihai Paun, I get a generalized KLT pair, which of course has dimensions smaller than the dimension of X. And it's easy to see that you can arrange that eta b plus eta is also a big class. So by induction of dimension, alpha restricted to V1 is semi-ample. Okay, so if the null locus was equal to V1, I would be done. I would have 1 at this point, right? I would have this map from the locus, from the null locus to W. So any questions so far? Okay, so unluckily, you do not, it could happen that V1 is just a point inside of a big, interesting null set. So you have to continue, and sort of the idea would be that you want to inductively extend to bigger and bigger subsets of the null locus until you hit the whole null locus. So you look for subsequent log canonical thresholds, and eventually the non-KOT locus will actually agree with the whole no locus. So suppose that we have inductively defined morphisms from VK to WK. So VK is the non-KOT locus of B plus beta X plus lambda K gamma. And these morphisms, of course, have to, by their definition, they have to contract all alpha trivial curves. And now we want to define it on the next locus, VK plus 1. Well, there's two possibilities. It could happen that the next strata to be included in the non-KOT locus is contained in VK. Well, then you have nothing to do. I told you I'm not interested in any scheme structure. Or it could happen that V prime is not contained in VK. Well, in this case, your pair, kx plus b plus beta plus lambda k plus 1 gamma, will actually be log canonical at general points of V prime, so you can do a junction along V prime, once again. You will not get a generalized KOT pair. The singularities of this pair will be concentrated on the intersection between VK and V prime. So alpha is already defined on this intersection. And the goal here would be to glue, so first of all, I would like to define a morphism on V prime and then glue it together with the morphism that I had already defined on VK. And this way I would have a morphism defined on VK plus 1. Okay, so for this to work, I actually have to prove a more general version of the transcendental base point free theorem. I need to prove something along the lines of I won't assume that my pair is generalized KOT, but I will assume that the morphism is already defined along the non-KOT locus. So this would be similar to a base point free theorem where you allow your pair to be, in the traditional case, you allowed your pair to be non-KOT, but you assume that the divisor that you're trying to show is semi-ample when restricted to the non-KOT locus. Now, such theorems do exist in the usual projective setting, so there's reason to hope, but what you use in that case is you use Nadeau vanishing, which directly tells you that you have surjectivity from sections of your divisor on the ambient varieties to section of the divisor restricted to the non-KOT locus. So if your divisor on the non-KOT locus is generated, then on the ambient variety is clearly generated in a neighborhood of the non-KOT locus. So that works very well. Here we don't have any divisor, we don't have any line bundle to extend sections, so it's definitely trickier. Okay, so assuming one can make that step work, then we would have, by induction, we eventually get a morphism defined from the reduced no locus to some space, complex space W. The next step is to extend this morphism to a formal neighborhood of N. So let me make that more precise. Let me, for simplicity, I'm going to replace xb plus beta x by a log resolution. So I'm going to assume that the no locus is in fact a divisor. And so here's the only thing that I'm sweeping under the rug is, when you pass to a log resolution, typically this boundary will not be an effective divisor. There'll be something with negative coefficients along some exceptional divisor. I don't want to have to keep track of that, so I'm just going to assume that b is greater or equal to 0. Beta x is nef, right? When you're going to high enough model, this 1-1 form becomes nef. And gamma is of the form f, where f is some effective R divisor, and omega is some Kähler form. And you can always do this as long as you take a sufficiently high resolution. So let's just assume that we've done that. And in other words, this f is going to be some simple normal crossing divisor supported on N. Again, for the experts, I'm hiding a small detail here, but I don't want to try to do the necessary bookkeeping. Okay, so what I want to do is I have a morphism that's defined on the reduced spaces corresponding to these non-Kawamata log terminal loci. So the non-Kawamata log terminal loci now corresponds just to the round down of the divisor B plus lambda kf. And I'm putting a tilde above this because this is now a non-reduced divisor. I'm keeping track of the multiplicities. Okay, so I want to actually now define these maps as morphisms from these non-reduced spaces. In order to do that, I will use Kawamata-Vivek vanishing. So I consider short exact sequences. When I increase from lambda k to lambda k plus 1, I pick up a new component of my non-KLT locus, a new divisor that I denote by V prime. And I have some short exact sequences which look like this. You can take the thickened space, Vk plus 1, restricted to Vk, and you can consider the kernel of that map, which looks like OV prime. It's supported on this new divisor that you've added, minus the round down of this divisor in order to make this sequence exact. Now, this is set up so that Kawamata-Vivek vanishing will hold relative to this morphism F. So I had this original morphism F defined on the non-reduced spaces. I view this as a short exact sequence of groups, and I want to use this to show that I have a surjectivity from F lower star of OV on the slightly thickened OVK plus 1 to F lower star of OVK. And this will show that the functions defining the morphism on the non-reduced space VK actually extend to functions on VK plus 1. So in this way, I'm extending the morphism to the corresponding thickening. And the whole point is that when I look at the short exact sequence, then Kawamata-Vivek vanishing does apply to the new divisor that I have introduced. So the upshot is that F extends to arbitrary thickenings of the no locus, and hence it extends to a formal neighborhood. And then in order to extend it to the whole of X, I have to use a result of Artin or Fujiki. So the setup is the following. I have my form alpha is trivial with respect to this map F defined on the divisor. Now, since alpha or gamma, they are equivalent, is of the form F plus omega, where omega is Kähler, then minus F restricted to the support of F is relatively ample, right? Because gamma becomes trivial with respect to this map. So this becomes a relatively ample divisor. So in particular, it's a projective morphism. And now this divisor, let's not worry about the fact that it's an R divisor. I can approximate it with a Q divisor. I can pick some sufficiently big integer k to clear the denominators. So I have a Cartier divisor supported on F. And since I know that this map F extends to any thickening of the no locus, to any thickening of F, then the morphism in fact extends to A itself. And since minus F restricted to the support of F is ample, minus A restricted to A is ample. And we can check that if I make K sufficiently big, then Ri F low star of OA minus JA is 0 for all I greater than 0 and J greater than 0. And then by result of Artin or Fujiki, I can extend F to a morphism from the ambient variety X to Z, where the restriction to A is F, and the restriction to the complement of A is just the identity map. And so I have been able to make this approach work in full generality in dimension 3, but there are several technical difficulties that I have not dealt with yet in higher dimensions, and I'm hopeful, but I'm definitely not close yet. So anyhow, that's one possible strategy, and that's what I hope might work in the future.
Thanks so much. Any questions for Christopher? So actually, I have one question. So is it possible to say one word where the technical complications arise in dimension 4 and higher?
So in my mind, the place that I am having so far the hardest time is the step 1. So in order to make this step 1, remember you have this no locus, and you're trying to sort of cover the whole locus with non-cover matter log terminal loci. And at each point, you're adding a new component of the non-cover matter log terminal loci. Now, the restriction to that locus will not be generalized KLT because it intersects the previous locus somewhere. So in some sense, you need to prove a more general theorem. You can't just prove a base point free theorem for generalized pairs, generalized KLT pairs. You need to prove it up to the non-KLT locus. That introduces a lot of bookkeeping, and then you need to be careful how you glue these things together. And things are not normal, for example, precisely along this locus where they intersect. So that creates some other technical difficulties. And it's not clear to me that it's not just a bookkeeping issue, or there really is some big difficulty hidden somewhere here. So, that's why I'm still a bit on the fence. The other steps, I know I've waved my hands a lot, but the other steps I'm fairly confident can be resolved. But if there's one place that I'm worried about, this would be the place.
I see. Thank you. Other questions or comments? Okay, if not, thanks again.